So in this video I'm going to be going over L'Hopital's rule, which is a method which allows us to find some limits that we would not have been able to calculate before. So in class I went over some explanation of where this rule comes from, but for the purposes here I think I'm just going to remind you what the rule says. So if f, g are differentiable functions, and a is any real number, or also it could be plus or minus infinity, then if we also have that the limit is in indeterminate form, meaning that limit as x approaches a, f of x equals plus or minus infinity, and limit x approaches a, g of x equals plus or minus infinity, or limit as x approaches a, f of x is equal to limit as x approaches a, g of x is equal to 0, then we have that the limit as x approaches a, f of x divided by g of x is equal to the limit as x approaches a, f prime of x divided by g prime of x. So in other words, we can take the derivative of both numerator and denominator and then take the limit. And so again, you can sort of get a rough justification of why this probably should be true using L'Hopital's rule, or I'm using linear approximations, but I'm going to just leave that as something you can look in the textbook or in the notes for. And we're just going to take this rule for granted and see some examples of how we can use it. So, as a first example, let's look at the limit as x approaches 1, x minus 1 divided by log of x. So, L'Hopital's rule is that we have an indeterminate form. So in other words, it should be a form of 0 over 0 or infinity divided by infinity. If we try plugging in 1, then you'll see that the numerator is 0, log of 1 is also 0, so in this case we have 0 over 0. We can apply L'Hopital's rule, and we can take the derivative of both numerator and denominator. So we'll get this equals the limit as x approaches 1 of 1 divided by 1 over x, which when you flip it is equal to the limit as x approaches 1 of x, and of just equal to 1. Okay, so this is the most basic example of L'Hopital's rule you can have. You have a limit of a quotient, which is an indeterminate form of infinity over infinity, or 0 over 0. You take derivatives and you get your answer. A slightly harder problem you can have is one where you have to use L'Hopital's rule multiple times. So if you look at this one, you'll see that you have an indeterminate form of infinity divided by infinity. So you can apply L'Hopital's rule and get this equals the limit as x goes to infinity of 2x divided by e to the x. But now we notice that this still has a form of infinity divided by infinity. So we use L'Hopital's rule again, and we get limit as x goes to infinity 2 divided by e to the x. Now finally we can see that as x goes to infinity, the numerator is constant, denominator goes to 0, so the overall limit is equal to 0. So there are other sort of forms that we can deal with using L'Hopital's rule. So, for example, suppose I want to find the limit as x goes to 0, x log of x. Well, notice that this is not in the form of a quotient, so it doesn't look like something we can use L'Hopital's rule on. But if we just try to plug in 0, we'll get 0 times negative infinity, which is a form that's not so easy to tell just by looking at it, because you have a really small number times a really big number. So in order to make progress on this, we rewrite it as the limit as x approaches 0 of log of x divided by x to the negative 1 power. And now we do have a quotient, and notice that if we plug in 0, it'll look like infinity divided by infinity. That means we can apply L'Hopital's rule and get limit as x goes to 0, 1 over x divided by negative x to the negative 2. And if you rearrange this a bit, you'll see that you get limit as x goes to 0 of negative x, which is of course just equal to 0. So even though it wasn't in a form we could use L'Hopital's rule on initially, with a little bit of manipulation we were able to get it there. Another trick you sometimes see with these sorts of problems are ones where you have a limit as x goes to infinity of x e to the negative x. So basically you have something that goes to infinity in the base, but something that goes to 0 in the exponent. So again, this is some sort of indeterminate form. So the trick we can do is write that this is equal to L. Now we can take the log of both sides and get that log of L is going to be equal to the limit as x goes to infinity, e to the negative x log of x. Or if we rewrite this, it's the limit as x goes to infinity of log of x over e to the x. And so now, as x goes to infinity, both numerator and denominator approach infinity. So we can apply L'Hopital's rule. We'll get limit as x goes to infinity of 1 over x e to the x. And this is, of course, equal to 0. So that means log of L is equal to 0. So it must be the case that L is equal to 1. So we can find this limit indirectly by first finding the log of the limit. So that's another trick you'll sometimes see. So the last thing I want to discuss with regards to L'Hopital's rule is what's known as function dominance. So we say that f of x dominates g of x if the limit as x goes to infinity, g of x over f of x is equal to 0. So another way of putting this is that f of x is much bigger than g of x as x goes to infinity, because the denominator grows much more quickly, causing the limit to be 0. So there's a general order to function dominance, which is roughly that exponential functions, things like e to the x, will dominate power functions. So things like x to the power p will dominate log functions. And so this sort of thing can be verified using L'Hopital's rule. So for example, let's suppose I want to compare a log function to a power function. I'd want to have to look at limit as x goes to infinity of x to some power over log of x. So this looks like infinity over infinity. I can apply L'Hopital's rule to get to this limit as x goes to infinity, px to the p minus 1 over 1 over x, which is the limit as x goes to infinity of px to the power p. And of course that's going to be infinity. So that means that if you were to flip this fraction, the limit of log of x over x to the p would be equal to 0. And so we can see that the power function indeed dominates the log function. And so this is a good rule of thumb. If you have some more complicated combination of these things, then you can use L'Hopital's rule to see which one is growing faster. And that can be useful since it should give you an intuitive idea of what the value of a limit is. So, I mean, for example, if I look at something like limit as x goes to infinity of x to the 1000 plus x to the 7 minus 3 over e to the x, then I immediately say that this is equal to 0 without any additional work, because I know that the exponential function will dominate the power function. So if you really wanted, you could use L'Hopital's rule a bunch of times to verify this, but having this intuitive understanding is really useful for limits like this.